Hi, I'm Herb Gross, and welcome to Lecture 8 in Gateways to Algebra, where we're going to be discussing a very important topic, sort of an enrichment topic, but important, called significant figures, and it deals with scientific notation, which in turn uses exponents with base 10. Let me just start off with a fairly simple question. Let's suppose you don't know how many people are sitting in the room, because I'm the only one who sees the room, so I make a statement, there are exactly 6 people in this room. That's a very easy statement to check. You simply count the number of people. If there are 6, that's fine. If there's less than 6, it's a false statement. If there's more than 6, it's false. What's interesting is the use of the word exactly. You see, can you have more than 5 people in the room and less than 6? I suppose if you could, you wouldn't want to see it. See, it's like the old joke about the Marine sergeant where the men were digging the latrine, and he says, how many of you guys down there? And the foreman said 7. And the sergeant said, half of you come on up. You see, even though 7 divided by 2 makes sense when we talk about fractions, there are times when answers have to be whole numbers. So can you have more than 6 people in the room but less than 7? The answer is no. You see, when you count, after 6 comes 7. And the only whole number before 6, the first whole number that comes before 6 is 5. There are no whole numbers between 5 and 6. There are no whole numbers between 6 and 7. But watch that's called a discrete variable because it's spaced. It's not continuous, okay? Let me give you an example of a continuous variable. Suppose instead I say to you, instead of saying there are exactly 6 people in the room, I say this piece of string is exactly 6 inches long. That may not sound like a tricky statement. Well, in some cases it's not. Suppose this is my ruler here. I take the piece of string, I start at the beginning of the ruler, and it ends over here. I can see right away that this is a false statement. Or I could have put the string over here, and it ends over here, well beyond the 6-inch marking. So this piece was shorter than 6 inches. This piece was longer. So for both of these pieces, this is a false statement. No problem so far. The problem comes up when the piece of string looks like it might be exactly 6 inches. See? Here's what we have now. Here's the 6-inch marking on the ruler. Here's the piece of string. I put it down at the beginning of the ruler. It seems to end on the 6-inch mark. And I say, this piece of string is exactly 6 inches long. Now here's the problem. The problem is, does this marking on the ruler have thickness? Or is it invisible? It can't be invisible. I can see that marking. And once I see it, it's an empty question to say, is it thick or is it thin? Because once I can see it, with the use of a microscope, I can make that thing quite large. Maybe with a powerful microscope, I can make this piece of the 6-inch mark this wide. And the piece of string now swells up to this size. And now take a look. See, notice that what looked like exactly 6 over here, this piece of string, we don't know where is the exactly 6-inch mark here. Is it at the beginning? Is it at the end? Or is it in the middle? And by the way, before you jump to answering this thing, you're better off if you say, what's the use? Suppose you say it's at the beginning. All I got to do is take a more powerful microscope and blow up the beginning. So now maybe the beginning looks like this. And so I say to you, is it the beginning of the beginning, the middle of the beginning, or the end of the beginning? And this goes on forever. Because if you say it's the beginning of the beginning, I blow this up again and say, is it the beginning of the beginning of the beginning? Is it the middle of the beginning of the beginning? Or is it the end of the beginning of the beginning? And after a while, you can see how difficult this is. Until you eventually say, what? Close enough. Close enough. I remember an old Sid Caesar routine where he plays the part of somebody called the Takeoff on Zorro, where he calls himself the Mark of Zero. And Imogene Coca says to him, what do you do for a living? He says, I rob from the rich and I give to the poor. He says, doesn't that make the rich poor and the poor rich? He says, yes, but then I rob from the rich who were once poor and give to the poor who were once rich. And he keeps on going this way, and finally he looks at it and says, what's the difference? I just keep the money in circulation. It's the same kind of a thing that we're doing over here. Once something is continuous, do you see what I'm saying? Can you have a piece of string that's longer than 5 inches long but shorter than 6 inches long? Yes, all sorts of lengths. That's called a continuous variable. Time is a continuous variable. An interval of time can be more than 1 second and less than 2 seconds. This problem occurs in calculus when we say how fast is something moving at a given instant. Let me give you another problem that may sound kind of simple. I'll just write the problem down over here, and I won't comment on it, but just think about it. Where was the man at the instant he jumped off the bridge? And the key word here is instant. You see, if the problem says, where was the man 1 second before he jumped off the bridge, that's pretty obvious. He's still on the bridge, isn't he? B will stand for on the bridge. Where was the man 1 second after he jumped off the bridge? He's in the air. But the problem says, where was the man at the instant he jumped off the bridge? You see, there's a unique moment of time where just before that, you're still on the bridge, and just after that, you're in the air. And you can zero in on that quite nicely, but it's not a very simple problem to do. I mean, for example, here's the time. I say, okay, at a particular time, where was the man? See, I measure at this time. He's still on the bridge. Well, if he's still on the bridge, it means he hasn't jumped off yet. Now I say, let me look a little while later. A little while later, I measure, and he's in the air. Well, if he's in the air, he's already jumped off. So the place he jumped off had to be between these two times. Now I can take another time. I say, where was he at this time? If he's still on the bridge, I know he hasn't jumped yet. So now he has to have jumped where? Between this time and this time. And you see what happens? I take another time. Suppose he's in the air over here. Well, that means he's already jumped. That means he's between here and here. You see what's happening? I can whittle this interval down until it's so thin that eventually I say, who really cares? I know it was someplace in here. And again, you're doing what? Rounding off, in a sense, to a level where you feel comfortable. You see, at one time, the ancient Greeks didn't believe that there were, what would you call them, irrational numbers. They believed that the fractions filled in the whole number line. And their argument went something like this. They said, okay, let's take the interval from 0 to 1. And we'll take the average of that. That's 1/2. So 1/2 is a rational number. It's a fraction. Now let's split the interval in half again. Let's split it in half again. Let's split it in half again. And you see what's starting to happen? These dots are becoming thicker and thicker together. And after a while, doesn't it look as if they've all run together? You say, this has filled in the whole line. Well, amazingly enough, there's a difference between the dot and the point. Not only is this whole line not filled in, you don't even have a third over here. Look at, the only fractions you have are what? Halves, half of halves, half of halves of halves. In other words, the only fractions you're going to have are what? Denominators, which are 2, 4, 8, etc. What happened to 1/3? And the answer is that 1/3 got caught close enough between two of these dots that we could not measure the error. That after a while, you say close enough. And here's how the scientist tends to tackle that problem. If you were back in the 3rd or 4th or 5th grade, wherever you learned decimals, how are the numbers 6, 6.0, 6.00, 6.000 related? Is 6.0 the same as 6? Like when you're in a grocery store and you write out a check, is it the same amount of money whether you write $6 this way or whether you write $6 this way? Those zeros don't mean anything, do they? See, the mathematician talks about exact numbers. And when you're talking about exact numbers, it doesn't matter whether you say 6, 6.0, 6.00, 6.000. It all stands for 6. Now, by the way, I don't want you to get the mistaken idea that I say it's impossible for a piece of string to be exactly 6 inches long. There is such a length as exactly 6 inches, isn't there? All I'm saying is you'll never know when that piece of string is exactly 6 inches long. You'll never be able to measure that close. You'll be able to approximate it, and you'll say, what? To as close as I can figure, it's 6 inches long. But there's always going to be that question of how thick is thick. You see, it's the difference between a dot and a point. You know, I sort of think of it philosophically in terms of talking about the present. You know, what is the present? And you can relate it to the past and the future. The present is that unique moment in time where it's the oldest that you've ever been, but the youngest that you're ever going to be again. And how you live your life may very well depend on which of the two ways you look at that. But you see what I'm saying? There is a point, but sometimes it's hard to pin down scientifically with exactness that you can measure. So with the scientists, you see, to the mathematician, the 6, the 6.0, 6.00 all mean the same thing. But to the scientist, they mean quite a bit more. When the scientist says 6.0, he's saying that the piece of string was 6 inches to the nearest tenth. And when he writes 6.00, he means it's 6 inches to the nearest hundredth. See, what he's saying is, here's 6. 1/100th more than 6 is 6.01. 1/100th less than 6 is 5.99. Halfway in between is what? 5.95, 6.05, 6.995, 6.005. And now what the mathematician, what the engineer is saying is, I don't know if this is exactly 6 inches or not, but I do know if you don't want anything closer than this. You see what I'm saying? Halfway between here and here, make sure you're closer to this one than you are to either of these two. And all the scientist is saying is, I don't know the exact answer, but I'm going to tell you how small the maximum error will be. And let me show you how this comes up, for example, if we were dealing with a typical high school arithmetic problem. An arithmetic problem might say something like this. Let me just get a fresh sheet of paper over here. They might say what? We have a rectangle that's 5.7 centimeters in length, and what's the number I have down here? 3.4 centimeters in width. What's the area of this rectangle? And what's the formula for the area? It's the length times the width. And I'm sure you never thought about this, but how'd you then do the problem? You said the length is 5.7 and the width is 3.4. So therefore, all I'm going to do is I will multiply 5.7 times 3.4, either longhand or with the calculator. You multiply this out and you get 19.38 square centimeters. Now, there's nothing wrong with this in a certain sense. In the pure math sense, what this says is, look, if the length was exactly 5.7 centimeters, and if the width was exactly 3.4 centimeters, then the area would have been exactly 9.38 centimeters. The problem is we don't know when something is exactly 5.7. So when the engineer or the scientist writes 5.7 centimeters, they're guaranteeing the measurement to the nearest tenth of a centimeter, which means a millimeter. In other words, let's tack a 0 on over here so we can see the numbers easier, because I almost messed that up on the previous example up here. See, 5.70, see, counting this way, before 70 comes 60, and after 70 comes 80. Halfway between 60 and 70 is 65. Halfway between 70 and 80 is 75. So so to be accurate to the nearest tenth of a centimeter, see, to be closer to 5.7 than to either 5.6 or 5.8 simply means you can be where? Any place between 5.65 centimeters and 5.75 centimeters. In other words, what the scientist is saying is that 5.7 guarantees that you're at least 5.65 and no more than 5.75. In a similar way, 0.40, before that is what? Before 40 comes 30, then comes 50. Halfway between 30 and 40 is 35. Halfway between 40 and 50 is 45. So what we're saying now is what? When the engineer says 3.4 centimeters, he's guaranteeing that the measurement is what? Somewhere between 3.45 and 3.35 centimeters, because if it was smaller than 3.35 centimeters, it would then be closer to 3.3 rather than 3.4. And if it was more than 3.45, it would be closer to 3.5. So now what the engineer says is, look, all I know for sure is that the 5.7 tells me I'm between 5.65 and 5.75. And the 3.4 tells me I'm between 3.35 and 3.45. In other words, to do this in yet another way, what we're saying is, let me see if I can just use these numbers again. What we're saying is that the length, I'm going to write this down a little bit better for you, the length is more than 5.65, but it's less than 5.75, and the width lies between where? 3.35 and 3.45. Therefore what? Whatever the length times the width is, it has to be more than this times this, and less than this times this, and that's what we're just saying over here. In other words, the worst situation, meaning the smallest area, would be if the two smallest amounts possible were present. That on the calculator would be 18.9275. The best case, meaning the biggest you could have, would be 19.8375 when you multiply these numbers together. Notice, by the way, obviously, that the answer that you get in grade school does fall between these two extremes. But in the world of science, all we're saying is, look, if you were sure that these numbers were exact, this would be the exact answer. But if you want to argue that these are only accurate to the nearest tenth, where you measured over here, then any number between 18.9275 and 19.8375 is as valid an answer as the 19.38. Okay? So I just thought you might like to see something like that. And you say, what does this have to do with exponents? You see there were no exponents in here? Well, basically, let me just give you some examples again. See what we're going to, you follow what we're doing so far? You see the difference between the world of discrete mathematics and the world of continuous mathematics? See, discrete means there's what? A smallest and a biggest and nothing in between. You can measure two and nothing in between. See, are there any whole numbers between 1 and 2? No. Are there any fractions between 1 and 2? Sure. 1.5. Yeah, okay. Any fractions between 1 and 1.5? Yeah, the average of that, 1 1/4. You can always find what? Between any two fractions, there will lie another fraction. That causes a big change when you're talking about measurement, and you have to be exact. Okay? See, so let me give you an example of what might happen. Have you ever seen a sign you're driving, and can you picture something that might say, or let's say, San Diego, 2,735 miles. Do you really believe when that sign says 2,735 miles that it is exactly 2,735 miles? Is it possible that it's 2,735 miles and 436 yards? Also, San Diego may look like a dot on the map, but it's a regular city, isn't it? Has different dimensions. What part, if it was exactly 2,735 miles, to what part of San Diego would it be measured to? You see, in other words, how accurate is this number? Do you really care if it's off by a mile? See, again, notice the accuracy question again. Think about that. You see, is a mile a lot? Well, if you're talking about the distance between Boston and California, a mile more or less I don't think makes that much difference. But if you're talking about brain surgery technology, even a 2-foot error may mean you're transforming the wrong brain. You may be in the wrong body. See, how close you have to measure depends on what problem you're dealing with. And by the way, that's where science is just as much of a social science and the humanities as anything else. How you measure accurately is one thing. The decision as to how closely you have to measure is quite another thing. And so these are the questions that we deal with. And what I wanted to show you is how we use exponential notation to sometimes measure how accurate a measurement is. So I thought I'd like to show you something like that. First, let me summarize for you what scientific notation is. Scientific notation is when you have a whole number that's between 1 and 10. I'm sorry, not a whole number. A number between 1 and 10, but the number can't be as big as 10. In other words, it could be 9.99, it could be 1, it could be 2.3, but it has to be what? A number that's at least 1, but less than 10, multiplied by 10 to an integer power. What are the integers? They're the whole numbers together with their negatives. The integers are 0, positive negative 1, positive negative 2, etc. So 7.3 times 10 to the 5th power would be in scientific notation because why? It's a number between 1 and 10 multiplied by 10 to a whole number power. And in fact, what would that number look like in place value? Okay, that number would look like what? To multiply by 10 to the 5th, that means you're multiplying by 10 5 times. That means you're going to have to move the decimal point 5 places to the right. there's only one digit to the right of the decimal point. To move it 5 places, you're going to need 4 placeholders. So it's what? A 3 and 4 zeros. That's 730,000. By the way, 730,000, couldn't that be written as 730 times 10 to the third power? See what I'm saying? If you took 730, how do you multiply by 10 to the third? Tack on 3 zeros. And again, if this sounds too fast for you, what's the rule we're talking about? Whenever you feel this way, back up the tape. You may decide, hey, I didn't study the last tape closely enough. Maybe I have to go back one more tape. I'm going to talk fast because I'm trying to give you as much information as possible, but unlike a live class situation, I'm assuming you have access to control buttons and to access to deciding when you're going to watch the next tape. And when you do watch the next tape, which the next tape is going to be. So don't use as an excuse, he's talking too fast. Okay? Make sure you understand the things I'm talking about. And then we'll go on from there, okay? So the idea is, see 730, 10 to the third means multiplying by, means 3 factors of 10. So multiplying by 10 to the third means I tack on 3 zeros. And you see what happens is both of these, both this and this stand for 730,000. The difference is this one here is scientific notation. This one here isn't. You see why it's not? Because this number here isn't between 1 and 10. And by the way, suppose, see, with 730,000, isn't it possible that I only measured this to the nearest 100 or to the nearest 1,000 or to the nearest 10? Who knows how accurate this number is? So let me show you how the scientist uses scientific notation. See, whether you're a scientist or not, how would you write this in scientific notation? It would be 7.3 times what? If the decimal point was over here, you want the decimal point really to be over here, so you have to move it what? 1, 2, 3, 4, 5. 5 places to the right. See, can you double check that for me? If I take 7.3, move the decimal point 5 places to the right, I get 730,000, okay? Now, all the scientist does is, suppose he wants to trust just 2 digits over here. To trust 2 digits, aren't the 2 digits already in here? See the 7 and the 3? Suppose he wants to indicate that it's accurate to include even this digit. Well, see, now what he does is, see, this is the part that he's vouching for, the 730. He puts a 0 after the 3. Now, if you write this out in scientific notation, in place value notation, 7.30 is the same as 7.3. The difference is, even though both of these look like this, when the scientist writes this, he's guaranteeing you accuracy for this many digits. If he wants to show you that all of these digits are accurate, what he'll write is what? How many zeros are there here? 4. So he'll put in all 4 zeros. Notice what's happening. He's not changing the exponent. He's just saying what? Instead of writing 7.3, I'll write it as 7.30. That tells me I have what? 3 significant figures. But if I write this, I have what? 1, 2, 3, 4, 5, 6. 6 significant figures. So in other words, even though all 3 of these would look like 730,000, this one tells the engineer that it's only accurate to the nearest 10,000. This one tells him it would be accurate to the nearest 1,000, and this one tells him it would be accurate to the nearest whole number. We have a minute or so left, so I thought I would like to make sure that you understand scientific notation again and how you write it. So let's just do that, and then we'll stop on that. You see, here's this number over here, 6,835,247. To make this in scientific notation, I want this number to be between 1 and 10, so I have to put the decimal point between the 6 and the 8. But it still has to be the same number. To get the decimal point back out here, I have to move it what? 1, 2, 3, 4, 5, 6 places, so I write it this way here. In a similar way, if I wanted to write this in scientific notation, I would still need a number between 1 and 10, so the decimal point would be over here, but I still have to represent this number here. That means I have to do what? Move back the decimal point 1, 2, 3 places to the right, So this would be 6.835247 times 10 to the minus third. I think for an enrichment topic, that's about enough for now. You see, what I wanted to do was to show you that as we're studying algebra, there are many, many serious problems that go beyond Algebra 1 that we tackle in subjects like calculus, subjects beyond calculus, but the roots lie where? In arithmetic and in elementary algebra. You see, and how something like exponents, which we use in Algebra 1 and in place value, can be extended in scope to deal with problems which are far more complex. This is not any different than English grammar, where a noun in the first grade means the same thing as a noun in graduate school. It's still what? A person, place, or thing. But as you go through the various years of your schooling, the nouns become more sophisticated. See, the concept stays the same, the application becomes more profound. And you can't understand the profound application unless you first understand the simpler ones. So let's rest on that for the time being. Study hard, enjoy, stay young.